Hello, everyone. This is Gaurav Goel, and welcome to today's session on AI-driven NTN satellite in 5G, 6G, a game changer. I hope you all are doing well and are safe. So, this is the agenda for today's session. So, we will address as much as possible within the next hour or so. The remaining topics will be continued in the next session. So, first, we'll start with NTN and the satellite fundamentals. Understanding what NTN is and how it extends connectivity beyond traditional terrestrial networks using satellites, HAPs, drones, etc. Next, we'll explore the use cases and requirements where NTN is used, such as remote connectivity, aviation, maritime, disaster recovery, IoT, etc. Also, we'll see its unique performance and requirements like latency, coverage, and reliability. Then we will analyze the 5G NTN architecture and deployment. So here we will see how satellites integrate with 5G networks, including components like G Node B, NTN gateway, 5G core, etc. After that, we will review NTN network operations, like key procedures like network access, registration, session setup, also how they are adapted to handle satellite specific challenges like delay and the Doppler effects. So we'll also evaluate deployment considerations like spectrum, link budget, propagation delay, mobility, and also overall design constraints for the NTN networks. Finally, we'll look at the AI, the intelligent core for 5G, 6G, and the NTN integration. So here we'll see how artificial intelligence enhances NTN enabled networks. So these are the various options for that. It can be through intelligent resource allocation, predictive maintenance, traffic optimization, autonomous network management. Our ultimate aim is smarter and more efficient global connectivity, right? So imagine a world where your network never drops, whether you are in city, an aircraft, or the middle of the ocean. So that is the power of NTN, AI, and 6G. All three will bring truly intelligent global connectivity. So stay with me because what you are about to learn can completely change how you understand telecom networks. Hi friends, it's good to see you all again. And this is Gaurav Goel. First of all, thank you so much for joining this session. Now, a quick introduction about myself. I have around 20 years of experience in the telecom industry, mostly in the wireless networks with a strong focus on RF design, planning, optimization, and the in-building solutions DAS. I had opportunity to work with leading telecom operators in US like AT&T, Verizon, T-Mobile, and Dish, as well as major global vendors such as Nokia, Ericsson, Samsung. So I've also worked with InfoVista, contributing to their Planet tool from a product and the solution perspective. And before moving to the US, I have worked for various international projects for various countries like India, Nigeria, Japan, Finland, and UK. So all had been gaining diverse and the global exposure in the telecom deployments. I started my career with 2G and now working extensively for 5G for several years. And for last few years, focus is on 6G, DAS, public safety, AI, NTN, etc. So that is why sessions like these are very important to stay updated, relevant, and ahead in the fast changing industry. So that is brief introduction about me. For more details, you can connect with me on LinkedIn, and I have already given you my LinkedIn profile in the chat box, so you can go there and check your LinkedIn profile, check my LinkedIn profile. And these are a few of my iCards. So these are not just iCards; these are the milestone of my journey in telecom. Each one carries a story of learning, challenges, and real network deployments from 2G to 5G, from terrestrial networks to non-terrestrial networks, and now evolving towards 6G, AI, etc. So together they form a treasure I deeply value. So when I talk about these technology, it is not just theory, it is built on real world experience. So, like in every webinar, let's quickly go through a few codes which I want to share with you. So, we often see success only on the surface. It looks easy and effortless, but behind it lies years of struggle and hard work. So, this is what we call the iceberg. illusion. So it means we notice a success, but not the effort that made it possible. So this is my favorite analogy for years. So we see the success, but not the work that went into it. We do not see their sacrifices, their good habits, their focus, their growth mindset, their working weekends. All these things we don't notice because success is like an iceberg. Nobody sees the work that comprises it. So what does success demand? Success demand hard work. Success demand patience. So patience. So if you're losing the patience, you are losing the battle because patience is a three-step process. First, nothing happens. Then it happens slowly, and then suddenly. But the problem is that most people give up at this stage one, right? So if you're losing the patience, you are losing the battle. Then you have sacrifice. So if you do not sacrifice for what you want, then what you want becomes your sacrifice. Everything has its price. The question, are you ready to pay it for the life you desire? So many of you are joining this session from different time zones. Some of you have sacrificed sleep to be here. That show your commitment, your growth and success. So sleep can be recovered, but opportunities like this should not be missed. Then we have consistency. So consistency is what transforms average into excellence. So without consistency, you will never achieve greater success. For example, I see some of your names in every session. You show up again and again. That is not luck, that is consistency. And consistency is what creates real success. So the first step towards knowing is to see what you don't know. So it means real learning begins with accepting your ignorance. So if you believe you already know everything, you stop growing. But when you honestly admit, I do not know this, your mind opens up and you become ready to learn, explore, and gain true knowledge. In short, accepting that you don't know is the foundation of wisdom. To get success, you don't have to see the whole staircase. Just take the first step and keep on working on that first step. So never lose your childlike curiosity. Always invest in yourself because that is what keeps learning alive. In today's fast changing world, being a lifelong learner is not an option. It is necessity, whether it is reading, taking courses, learning from mentors, or trying new things. Every step adds value to your growth. The most common investment you can make is in yourself because the highest return you will ever get is from continuously upgrading your knowledge and skills. All right, so that is enough of motivation. So let's move to the main topic. So we have already discussed the agenda for the session. So let's jump to the topic one, which is satellite and the NTN Foundation. So satellite communication overview. So let's start with basics of satellite communication. So what is satellite? A satellite is simply an object in space that orbits around a larger object. In our case, the Earth. So what is satellite? So in simple terms, a satellite moves around the Earth in a fixed path called orbit. So now when we talk about communication system, we are mainly referring to the artificial satellites. An artificial satellite is a man-made object placed in orbit. Its main role is to relay and amplify communication signals. So what happens? So instead of signals traveling directly over long distances on Earth, they are sent to satellites and then back to another location. So this allows communication over very large distances, even across continents and oceans. It also enables connectivity in remote areas where terrestrial networks are not available. So let's look at now let's look at some of the applications. So first one is voice and telephony services. So it enables broadcasting of TV and radio signal worldwide. Then you have internet and data connectivity. So it provides internet connectivity, especially in the remote areas where signals is not easy to reach, where it's not difficult to install towers, fibers, etc. Then you have navigation, GNS, and GPS. So what is GPS? What is GNSS? So GPS, everybody know. So GNSS is Global Navigation Satellite System. Okay, we'll discuss in detail about GNSS in the next few slides. Then we have scientific and space research. So uh, NTN helps in space research and the data collection. And then you have weather monitoring. So it helps in meteorology. So it is used for weather forecasting and the climate monitoring. In short, you can say that satellite plays a critical role in enabling global communication. They extend connectivity beyond geographical limitations. So let's talk about some of the advantages and the disadvantages of the NTN networks. So now we have already seen what satellite communication is and at high level how it works. So let's see what are the main advantages and what are the main limitation of the satellite. So let's start with the advantages. So one key advantage is that the cost is largely independent of the distance. So whether the communication is local or across continents, the cost remains almost same. Then we have it is very useful for the remote location where it's difficult to have fibers or towers, right? Then we have short-term requirements. For example, temporary communication requires extremely useful during emergencies. So for example, during floods, most cell towers and fibers network get damaged or completely shut down. So in such situations, satellite-based networks can be deployed quickly to restore connectivity. These solutions help rescue teams coordinate, right? It helps hospitals stay connected. Moreover, with the help of this NTN, people can reach their families even in case of disasters, floods, or you can say that right now, even in the conflict zones, like in Iran, right? Right now, war is going on in Iran. So where infrastructure is destroyed, these systems provide instant communication support. So that is why for temporary needs, these are very cost effective and they have no need to invest in permanent infrastructure. After that, it helps in mobility as well. So they can provide connectivity to moving platforms like ships, aeroplanes, vehicles, etc. Moreover, satellite communication is highly adaptable. It supports multiple services like voice, video, data, etc. And then we have some of the limitations as well. The first limitation is that initial cost of equipment like antennas, terminals, which can be very, very high, right? The second disadvantage is that it has limited frequency spectrum. So this creates constraints on capacity and the scalability. As you know that in case of 5G, it can go maybe 52.6, right? But here it's not like that. It will not go beyond maybe 6 gigahertz or so on, right? We'll discuss in next few slides the spectrum. But in case of 5G, it can go up to long wavelength, right? So it's not that scalable or it has constraints on capacity, right? So as you know that in 5G we have from 400 to 7 gigahertz, and then we have up to as like 24.2 gigahertz to 52.6 gigahertz. But in case of NTN, it may not be possible because of long distance. Then we have this electromagnetic interference. So satellite signals can be affected by power lines or other communication systems. One more limitation is very important limitation of NTN is environmental sensitivity. So rain, snow, or any kind of solar activity can degrade signal quality. So this is often referred to as rain fade or atmosphere attenuation. So satellite communication offer unmatched global connectivity and flexibility. But it also comes for with challenges like cost, interference, and the environmental effect. In one line, you can say that satellite communication enables global reach, but requires smart design to overcome its limitations. Then you have satellite communication fundamentals. So now let's understand how satellite communication actually works. At a high level, the goal is to create a communication channel between transmitter and a receiver. So what is the basic working principle? The source transmit a signal to the satellite. The satellite then rebroadcasts that signal back to the earth. And the receiving station captures that signal. So essentially, the satellite acts as a relay in the space. So there are two types of communication possible. One is one-way communication. Second is two-way communication. Okay. So let's start with one-way communication on left side. So in this case, there is a single source sending data to one or multiple receivers. A common example in this case can be satellite television, right? So TV station transmit a signal to the satellite and millions of users receive it simultaneously. In this case, the communication only in the one direction from source to users. Then you have this two-way communication. So in this case, both stations can transmit and receive signals. One station sends an uplink to the satellite sends a downlink to the other station. And the same process happens in the reverse direction as well. A great example is internet connectivity. So in case of internet, both sides exchange data continuously. So this creates a point-to-point communication link. So satellite communication works by relaying signals between the ground stations. So it supports both one-way and two-way communication models. And this flexibility enables a wide range of applications, right? So two options, one-way communication and two-way communication. And examples of one-way communication can be satellite TV, and example of two-way communication can be internet. Then we have satellite communication signal flow. So now let's understand how communication happens between Earth station and the satellites. So as we have seen earlier, the basic function of Earth station is to transmit and receive signals. So first thing you have to discuss here is the uplink Earth station. So you know very well what is uplink and what is downlink. So when an Earth station sends signal to the satellite, it is called uplink. The Earth station converts information into a signal and transmits it towards the satellite. Before transmission, the signal is amplified to ensure that it travels long distance. Then you have satellite processing. So once the signal reaches the satellite, it performs several key functions. It receives the signals, it amplifies it converts to a different frequency, and then retransmit back to the Earth. So this enables communication over large distances. Then you have this downlink Earth station. So as we know, when the signal is sent back from satellite to Earth, that is called downlink. The receiving Earth station captures the signal and recovers the original information. One important concept you have to keep in mind is the signal loss. So when you talk about NTN, signal loss is very important. You always think of it. So as the signal travels through space and atmosphere, it experiences various losses. This includes path loss and the environmental effects such as rain and snow. So to compensate, the signal is amplified before transmission and after reception. So to maximize signal strength, the energy is focused into a narrow beam. So this is achieved using highly directional antennas. So both satellites and Earth stations rely on these antennas for the efficient communication. So in a nutshell, we can say that proper amplification and directional antennas are essential to overcome the signal losses. Then we have this parabolic antennas. Now let's understand one of the most important antenna types used in satellite communications, that is parabolic antennas. So parabolic antenna use the curve reflector. So this is the reflector to create highly directional beam. So what the basic principle? The key concept is this parabolic geometry. This is called the feed source. This is the feed source and is also called feed horn. So it is placed at the focus of this parabol. So when radio waves are transmitted, they are reflected off the curved surface and they are directed into this narrow focus beam. Suppose rays are coming like this, rays are coming like this. So they are focused into this feed horn. Now similarly, incoming signals from the specific direction are reflected back to the reflector, right? Feed horn signal are reflected back to the reflector. So this is the feed horn and this is the reflector. The reflector is typically made up of this is made of generally metals, but sometimes to save money, people use like lightweight materials with a metal coating, right? So generally these are made of metal, but to save money, people can coat this with the help of metal coating. The purpose of reflector is efficiently bounce radio waves towards or from the feed. One of the most important characteristics of parabolic antenna is gain. So gain increases with the size of the reflector and the frequency of operation. This means larger antennas or higher frequency results in more focused and the stronger signals. Right? So antenna gain is very important in case of parabolic antennas. Again, parabolic antennas use parabolic geometry to focus and reflect radio waves into a narrow beam. And we have seen that this thing is called feed horn to focus the signal, and this is called reflector. And you can see that when the reflector size is low, the gain is low. When the reflector size is large, gain is large, right? So low frequency, smaller reflector, mid frequency, medium reflector, and high frequency, large reflector, right? So these things you have to keep in mind when designing a parabolic antenna for the NTN networks. In short, you can say that parabolic antennas use geometry to focus radio waves into a narrow beam. This enables high gain and long distance communication, making them essential for the satellite communication. Then you have satellite frequencies and bands. So this is one of the most critical aspects of satellite communication, which is frequency bands. So different frequency bands are used depending on application, depending on coverage, and depending on the performance requirements. So let's look at some of the commonly used satellite bands. So first one is the C band. This operates between 4 and 8 gigahertz. So it offers strong reliability and is less affected by the weather conditions because it works in a low frequency band. Then you have X band. It works between 8 to 12 gigahertz. It is mainly used for military and specialized application. Then you have Ku band that operates between 12 to 18 gigahertz, and it is widely used for satellite TV and the broadband services. Then you have Ka band, which is between 26 to 40 gigahertz, and this is one of the most important band because it supports high data rates. Right? So let's see the trade-off. So as we move from lower to higher frequency, throughput increases, right? This means higher frequency bands can carry more data, right? As we move from lower to higher, throughput increases, but antenna sizes decreases as we move from higher to lower, and available bandwidth increases, right? Here we have lower bandwidth. As we move towards K, we have higher bandwidth. Then you have this rain fade effect. So when you are in C band, rain fade effect may be less. But as you move towards the Ka band, rain fade affected will be high. So rain fade is one of the most important challenge in case of NTN. So as frequency increases, susceptibility to rain fading also increase. Higher bands like Ka are more affected by the atmospheric conditions. Lower bands like C bands are more robust and reliable in the harsh weather. So from a system design perspective, selecting the right band is a trade-off, right? You have to lose something to gain something. So lower frequencies provides reliable coverage, right? So C band provides reliable coverage and high frequency provides high capacity. So the optimal choice depends on the application requirements. In simple terms, satellite frequency bands define how efficiently communication system perform. So each band offers a balance between coverage, capacity, and environmental impact. Let's talk about Earth station and the communication platforms. So Earth stations is one of the most critical part of the satellite communication systems. Earth station act as an interface between users on the ground and a satellite in space. So what is Earth station? So an Earth station is responsible for transmitting signals to the satellite and receiving signals from it. So it enables communication between terrestrial networks and the space-based systems. So there are different types of Earth station based on their deployment and mobility. The first type is fixed stations. So the fixed stations are the permanently installed at a specific location. They are typically used for gateways, broadcasting, and the large communication hubs. So these systems offer high reliability and large antenna sizes. Then we have this portable station or flyaway. So portable stations are designed for quick deployment in case of like disaster recovery, emergency response, and the temporary communication systems. So they provide flexibility when it's difficult to install a permanent infrastructure, or you can say when permanent infrastructure is not available. After that, we have SOTM, satellite on the move. So SOTM provides communication while the platform is moving. So these are used in dynamic environments where continuous connectivity is required. Examples can be ground vehicles. So it is used for connected cars, military vehicles, and the mobile command units. And then you have this maritime. It can be used for ships, cargo vessels, and the offshore operations. Then you have this airborne, and it can be used for aircraft connectivity and in-flight communication systems. So put simply, from a system perspective, the choice of Earth station depends on mobility, application, and the performance requirements. So fixed station focus on capacity and the stability. Portable and SOTM, satellite on the move, focus on flexibility and mobility. In summary, Earth stations are essential for connecting users to the satellite networks. So, Earth station brings satellite communication to life by connecting space networks to the real world application, right? So, these are the different types of the Earth station. So, now the question comes, what is non-terrestrial networks or NTN? So, let's see what is NTN. Before moving to NTN, any questions? Can you write in the chat box if you have? If you no questions, you can write no questions. Okay, thank you. So let's see again what is non-terrestrial networks. So NTN extends traditional telecom networks beyond the ground by using aerial and space-based platform to provide connectivity everywhere. So have you wondered like how connectivity works in aeroplanes, oceans, and remote mountains where there are no towers? So that is exactly where non-terrestrial networks NTN come into play. So let's begin with what we already know, traditional terrestrial networks. So these are the cell towers, right? These are the cell towers, right? So, but these cell towers have some limitations, especially in remote or hard to reach area. So here you have traditional terrestrial networks. So NTN complements this by adding connectivity from sky and space, especially where towers are not feasible, like remote areas, oceans, and the mountains. Then you have this air to ground network, air to ground network. So now moving one level up, aircraft at around 10-kilometer altitude connect using air to ground links. So this is what enables Wi-Fi in the airplanes. So this enables Wi-Fi for passengers at around 10 kilometers, right? Then you have this drones and this UAV. So what is UAV? So UAV is basically unmanned aerial vehicle. And what is UAS? This is unmanned aerial system, right? So close to the ground, we have drones operating at around 150 meters. And use cases can be, in this case, can be emergency coverage, like in case of disaster recovery, temporary network boost, like in case of events, we have lots of congestion. So it can temporarily improve our capacity because they act like flying small cells. Next comes the most important parts called the HAPS, which is high altitude platform station at around 20 kilometers. So these are the airships or balloons stationed in the stratosphere. You know, there are various layers, right? We'll talk about that later, but there are various layers in the environment like troposphere, stratosphere. So first is like troposphere, then we have stratosphere, then you have this mesosphere, then you have thermosphere, and then you have this exosphere. Right? So there are various layers. So this airborne satellites works in the stratosphere, right? So what are the key advantages of these HAPS? Because they have wide coverage than drones. So it can be used for large amount of coverage with this small numbers of HAPS. And it provides low latency as compared to satellites. And finally, we have these satellites, GEO, LEO, and the MEO. And they operate about 300 kilometers or above. So this is what enables global connectivity even in oceans, deserts, and the and the remote regions, mountains, etc. So this is very critical for 5G, 6G, NTN integration. So if you look at the scale on the right, you can clearly say how each layer is positioned. So around 150 meters, we have drones. Around 10 kilometers, we have aircraft. At 20 kilometers, we have HAPS, high altitude platform station. And then beyond that, we have satellites around 300 kilometers, right? So you can say that as we go higher, coverage increases, but latency also increase, especially in case of geo satellites, right? So NTN, you can say, is not a replacement for ground tower. It is just an extension. It integrates ground, air, and space to create seamless global connectivity. So from towers to drones to satellites, NTN connects everything and everywhere. Then we have platforms for non-terrestrial networks. So have you wondered why some satellites are fast, some are slow, some have less coverage, some have high coverage? This is because not all NTN platforms are the same. They operate at different altitudes with different performance characteristics. So in this slide, you can see the comparison of NTN platform from drones and HAPS all the way to the satellites. So we'll see how altitude directly impacts delay, coverage, and the deployment strategy. So let's start with the lowest altitude platform, which is HAPS and unmanned aircraft system. So their altitude is between 8 to 50 kilometers and their latency is less than 30 ms. And but their footprint size is very less, just 5 to 200 kilometers. Next is LEO, which is low Earth orbit. This is the one of the most widely used NTN layers as of today. So their altitude is between 300 to 1500 kilometers and their latency is around 30 ms, not very like higher than HAPS. And but their footprint size is very high, like around 1000 kilometers. But the problem is that we need large number of satellites for LEO between 50 and 100. Okay. So this is a sweet spot balancing latency and coverage, which is why LEO is heavily used for the broadband services. Then we have MEO, which is medium Earth orbit. So their altitude is between 7,000 to 25,000 kilometers, and latency is like three times of LEO, which is 90 millisecond. But their footprint is around the same as LEO, but their orbital period is very high, which is 2 to 8 hours. But they require less number of satellites, just 10. So these provide larger coverage with moderate latency, right? Then we have this GEO, which is geostationary Earth orbits. So it's positioned very high above in Earth. Their altitude is between altitude around 36,000 kilometers, but latency is very high, which is 140 millisecond, and footprint size is around 3,500 kilometers. but they require very less number of satellites as compared to the LEO, right? And then you have this high elliptical orbit HEO satellite. So their range is up to 50,000 kilometers, but latency is larger than 140 ms, and it requires just two satellites, right? So these are designed for areas where geo coverage is not possible, like polar regions, right? So if you observe carefully, as altitude increases, coverage also increases, but latency also increases. So this is a fundamental trade-off in the NTN design. No single NTN platform is perfect. Each one is optimized for a specific balance of latency, coverage, and capacity. So you have to balance between coverage, latency, and the capacity. Right. So let's move to our second topic, which is use cases and the requirements. Let's see what are the applications for the NTN. So you can see in this slide how NTN is transforming multiple industries by extending connectivity beyond traditional limits. So now let me ask you something. Have you ever wondered how smart cities, remote healthcare, or even disaster zones connected when terrestrial networks fail or are unavailable in case of wars, floods, or any other natural calamity, right? So that is exactly what NTN becomes a game changer. So let's start with first use case, which is IoT and the smart cities. So there are more than 2.5 billion connected devices, and they are increasing every day. So with NTN, we can enable connectivity not just in cities, but also in the remote and the rural areas. The use case can be smart sensor for traffic and infrastructure, environmental monitoring, and the agriculture use cases. So NTN ensures that smart city benefits are not limited to the urban areas only. Then we have this remote healthcare. So this is one of the most impactful application of NTN. So here use cases can be remote patient monitoring, telemedicine, and the virtual consultation. So even in the remote villages or disaster hit areas, doctors can connect with the patients in real time. Now let's look about the disaster response. In emergency situations, terrestrial networks are often the first to fail, right? Sometimes fiber can be cut, sometimes towers are down. So NTN can provide connectivity for emergency responders, drones for surveillance, and the damage assessment. So NTN provides instant, reliable communication when it matters the most. Then you have aviation and the maritime. So this is where NTN is already widely used today. So use case can be in-flight, Wi-Fi for passengers, connectivity for ships in the middle of oceans, and cargo tracking and the fleet management. So whether you are flying at 35,000 feet or sailing in the deep oceans, NTN keeps you connected. And finally, we have this military and defense. So this is one of the most critical use cases. So here examples can be secure and reliable communication, real-time video and drone operations, situational awareness in remote or the hostile environments. So in short, you can say NTN ensures mission critical connectivity with high reliability and the security. So NTN is not just about connectivity, it is about enabling applications where traditional networks can't reach. So it brings connectivity to the sky, the sea, and the most remote parts of the world. And what makes NTN a key pillar for 5G and even for 3G? So these numbers clearly show one thing. NTN is not just about coverage, it's about scale, speed, reliability, and the real world impact across industries. But NTN has various key challenges as well. So, what are the various key challenges? So, first one is long propagation delay. Like, so since satellites operate at a very high altitude, especially geo, the signal has to travel a long distance between the user and the satellite. So this results in the higher latency compared to the terrestrial networks. So this delay impacts real-time services like voice, gaming, and the interactive applications. Next is the larger Doppler shift. So due to high speed of satellites, especially in LEO, the frequency of signals changes dynamically. So this can affect synchronization and the signal decoding. So advanced compensation techniques are required to maintain the reliable communication. Then you have this frequency planning. So since multiple satellites and beam operates simultaneously, efficient spectrum allocation is very much required. So proper planning should be there to avoid any kinds of interference and to have optimal use of the available spectrum. Then you have this service latency. As I said earlier that distance between satellites and Earth station is very large. So managing latency is very essential to ensure quality of service, right? Then you have mobility patterns. So you have to take care of handovers and your tracking mechanisms. After that, you have your link budget. So due to long distances and atmospheric losses, signal strength can degrade significantly. So you have to take care of proper link budget, proper antenna gains, and the system designs are needed for reliable links. After that, you have this resource management. So this involves efficiently allocating spectrum, power, and capacity across users and the services. Since NTN supports diverse use cases from IoT to broadband, dynamic and intelligent resource allocation is required. The bottom line is NTN brings significant advantages, but also introduce unique challenges. These includes like latency, Doppler effects, mobility, resource optimization. So understanding and addressing these challenges is very much required, or you can say is a key for efficient building and the reliable NTN systems. Next, we have to jump to 5G NTN architecture and deployment. Now we have seen enough of theory of like advantage, disadvantage, how it works. But now let's see why my pen is not working. 5G NTN architecture and deployment. Before explaining this figure, let's recall 5G architecture at high level. You know very well that in 5G we have UE. UE is connected to G node B with the help of NRUU, or you can say that N1 interface. And then we have 2PF, which is connected with the help of N3 interface. And then we have data networks, which is N6. And G node is connected to the AMF with the help of N2 interface, right? This you know very well. This, but just to recall, this is very important because when we go to NTN architecture, this is very much required. Moreover, as you know that we have antennas, and then we have this G node BDU. This is also called like front haul. So these terms we'll use in next few slides. So we should remember the 5G also. So after that, we have G node B CUCP, and then we have this G node B CUUP. And as you know that it is connected with the help of F1C, and it is connected with the help of F1U. And then with the help of N2, it is connected with the help of AMS in the core. And here with the help of N3, it is connected with the help of UPS. And this is called like the mid hall, and this is called the back hall, right? And this is the core. Okay. Yeah, core has various other components as well, but uh, AMF and UPF are the important components. And before jumping, you have to learn some of the links which are very important. We will discuss in detail in later. So we have various links like service link, we have inter-satellite link, and we have the feeder link. So we have service link, we have ISL, and we have feeder link. Okay, so we have service link, ISL, and the feeder link. So service link is the radio interface between the satellite and the user equipment. For example, a smartphone, IoT device, or vehicle terminal. It is also known as the user link, and it is linked through which end user actually access 5G NTN services such as voice, data, or the IoT connectivity. So service link handles both uplinks like from UE to satellite and from satellite to UE, right? Then you have this feeder link. So this links connect the satellite to the ground gateway station, NTN gateway. So which then connects to the 5G core network. So it carries aggregated data between the core networks and the satellite. So this link is not directly accessible to the users. It is purely used as the network infrastructure. And feeder links typically operate at higher frequencies and require higher capacity backhaul. And then you have this ISL inter-satellite link. So inter-satellite link enables direct communication between the satellites. This will allow data to be routed through space without immediate ground station involvement. So these operates in the sky, right? This inter-satellite link. Now let's talk about non-terrestrial network architecture. So here you see two types of architecture approaches in case of NTN. One is transparent payload and one is regenerative payload. So both approaches define how signal processing is handled between the satellite and the ground network. So let's start with the transparent payload. This is also called the bent pipe architecture. So in this model, the satellite acts just like a relay. It will not do any kind of processing. It simply receives the signal from the users and forwards towards the ground station without processing it. So here the user connect through the NR-UU interface, right? And signal goes to the satellite and through the feeder link to the NTN gateway, and processing happens in the ground, at the ground, like DUCU, right? So G node B processing happens in the ground. No processing happens in the satellite. So this means simpler satellite design, but the signal has to travel a long distance to the ground and the back. So what can be an impact? Higher propagation delay and increased latency, but it is usable for basic connectivity, right? So for basic connectivity and less cost, transparent payload is the good use case. Then we have this regenerative payload. So in this case, part of the base station functionality is moved to the satellite. So processing can be done in the satellite as well. So here satellite performs signal processing on board, right? So communication with ground is through F1 interface, right? So ground station handles G node to CU and the core network. So what are the benefits of this? So some intelligence is now in this space. So this reduces the need to send everything back to the ground. So what is the impact? Like low propagation delay, improved latency as compared to the transparent payload. So notice the altitude, like in transparent payload, the altitude is around 36,000 kilometers. But in case of the regenerative payload, it is around 8,000 kilometers. So lower altitude in case of regenerative payload plus on-board processing leads to the better performance in case of regenerative payload. So transparent payload is simpler but introduce higher delay, right? And this regenerative payload is highly advanced. It reduces latency and support next generation NTN capabilities. And this shift towards regenerative architecture is the key for enabling 5G and 6G NTN networks. In short, you can say that now we are moving from satellites to intelligent space-based networks. Then you have this NTN architecture overview. So here you can see high level view of how NTN integrates with the 5G architecture. So it shows how device connect through satellites into the NG-RAN, then into the 5G core network. So let's start from the user side. So user side or user device is GNSS capable. As I said earlier, GNSS is global navigation satellite system, right? So this means it can determine its position using satellite navigation systems. This is very important in NTN because the network needs accurate location information for the communication and the tracking. The communication between the user and the satellite happens over the service link, as we have already mentioned. This uses 3GPP defined satellite bands, which I have already discussed. So this is similar to air interface in the terrestrial networks like 5G, but adapted for the satellite communication. Now we move to the NTN radio access network. We can say that this is the NTN radio access network. So this includes the satellite and the NTN gateway. So the satellite connects to the gateway using a feeder link, and this is also called SRI, satellite radio interface. So the link operates on a different frequency bands compared to the service link. At the ground station, we have NTN gateway and we have the G node V. So the G node V perform radio access network functions similar to the terrestrial 5G. So this is where satellite-based communication integrates with the standard 5G network. So overall, NTN integrates seamlessly into the 5G architecture by extending the RAN into this space. The user connects through satellite, but the core remains the same, right? So this enables global connectivity using 5G standards. Now let's talk about how to control beams in the NTN. So beam management is critical in NTN because satellites are moving and coverage needs to be maintained continuously. So there are two main approaches here. There are two approaches. One is fixed earth coverage beams. Second one is moving coverage beams. So let's start with earth fixed beams. In these beams, the beams are fixed on the earth surface. Even though here the satellite is moving, the beam stays locked to the specific geographical location. So how it works? So beam continuously tracks the location of this mobile station, for example. So if the mobile is moving, the beams are also moving. So here beams continuously tracks a fixed location on Earth, and satellite adjusts beams direction dynamically. So what are the advantages of this approach? So first of all, stable coverage for users in this specific area. Moreover, no need of frequent handovers as station moves from one place to other, right? As this UE moves from one place to other, there is no need of handover because this is controlled by only one satellite. But there are some challenges as well. So it requires very complex beam steering and tracking, right? This process is very complex and it requires higher processing complexity, right? So these are the few disadvantages, but this is very useful when we require less number of handovers. So now look at the Earth moving beams. So in this approach, the beams move along with the satellite. So the coverage area shifts continuously across the Earth. So how it works? So beam footprints moves as the satellite moves. So what are the key advantages? Key advantage is that it is easier to implement as compared to this fixed beams. But the various disadvantages as well, like we have frequent handovers, right? Frequent handovers are required in case of this moving coverage beam. So in Earth fixed beams, user experience more stable connectivity. But in Earth moving beams, user may experience handover problems similar to when we move from one cell tower to other. So what are the use cases of these two beams? So Earth fixed beams are preferred for the stable services. These are preferred for the stable services. But Earth moving beams are commonly used in the LEO. In the LEO orbits, we use this moving coverage beams. So you can say that Earth fixed beams provide stability but require advanced tracking. And Earth moving beams are simpler but requires efficient mobility management. And both approaches depends on various use cases, various system design, and other requirements. But there is one more beam which is called quasi-fixed beam control in NTN. So this is the balance of fixed beams and the moving beams. It combines the benefits of both earth fixed and the earth moving beam concepts. So what is the concept here? In quasi-earth fixed beams, the beam is not perfectly fixed, and but it is not also fully moving. It stays approximately fixed over a region for a certain duration and then gradually shifts. So from the user perspective, the beam appears almost stationary. So how it works? The satellite dynamically steers beam to follow a region on Earth for a limited time. This is the most important thing, for a limited time. As the satellite moves, the beam is slowly adjusted or handed over to the another beam. So this creates a quasi-fix. So what is a quasi-fix? It means almost fixed, but not completely permanent or rigid. So this approach reduces the number of frequent handovers compared to fully moving beams. It provides more stability connectivity to the users. At the same time, it provides high complexity of perfectly fixed beam tracking. But it also has some challenges, right? It still requires beam coordination and the intelligent control, right? And some handovers are still needed, though they are less frequent. So it requires advanced scheduling and the beam management algorithm. So you must be thinking where it can be used. So this approach is commonly used in LEO, right? Especially where there is a need to balance performance and the complexity. So in a nutshell, quasi-earth fixed beams strike a balance between stability and flexibility, right? So they reduce handovers while maintaining manageable system complexity. So quasi-earth beams offer the trade-off between the performance and the complexity in the NTN beam management. Then we have this 5G NR interface for NTN. Before understanding, let's recall the features of 5G. As you know that in 5G, we have flexible transmission bandwidth. So the bandwidth can range between 5 megahertz to 400 megahertz. Then you have this flexible subcarrier spacing. As you know that this is one of the most important feature of 5G. It can have subcarrier spacing of 15 kilohertz. It can have 30, 60, 120 and 240 kilohertz, right? And then you have this frame timings, right? it has it can be it can have 0 slots per subframe, or it can have up to 16 slots per subframe. Then duplexing, it can use FDD duplexing or TDD, time division duplexing. And then you have channel coding. As you know that in case of LTE, we use turbo coding, right? But turbo coding is now replaced by the polar coding. And then you have this LDPC, which is low density parity check. In case of LTE, we have what you call convolutional coding, right? So these are replaced in 5G with the help of polar coding and the LDPC. Then modulation. In case of 5G, very high modulation can be supported up to 256 QAM, right? So these features we should remember before jumping to the NTN features. In addition to that, as you know that 5G can be deployed as a standalone mode as well as non-standalone mode. So in case of 5G, various options are possible. Like in standalone, option 1 is possible, option 2 and option 5. In case of non-standalone, we have various options like option 3, 3A, 3X, option 4 and the option 7. Then we have 5G air interface for the NTN, right? So now we have recalled 5G. So we should know about the 5G air interface for NTN. So while NTN uses standard 5G technology, certain parameters are optimized to handle the satellite specific challenges like delay, we have Doppler effect, we have coverage, right? All these things we have to take care. So NTN primarily operates in the sub 6 gigahertz, sub 7 gigahertz spectrum, right? So this includes roughly between 410 megahertz to 7 gigahertz. So lower frequency are preferred because they provide better coverage and signal penetration over the long distances. Then you have duplexing. Mostly they prefer FDD. So each of us know that. So each of us know that duplexing defines how uplink and downlink transmissions are separated. So in NTN, mostly FDD is used. So this allows simultaneous uplink and downlink, which is important for maintaining stable communication over long distances and less interference as compared to TDD. Then you have channel bandwidth. So maximum channel bandwidth supported here is 20 megahertz, right? This is mainly due to spectrum constraints and the satellite system limitations. So compared to terrestrial, 5G NTN operates with a lower or narrower bandwidth. Then you have dual connectivity. So NTN also supports dual connectivity between G node B and NTN G node B. So this means the user device can connect to both terrestrial network and the non-terrestrial network simultaneously. So this provides reliable and ensures seamless service continuity. Then we have flexible subcarrier spacing. As you know that in case of 5G, it can be up to 240 kilohertz, but here it supports up to 60 kilohertz. So this flexibility helps manage Doppler effects and delay variation in the satellite communication. Then you have this modulation. In 5G, maximum modulation can be 256 QAM, but here maximum can be possible 16 QAM. So lower modulation ensures reliability, while higher modulation improves data rate when conditions allow. So 5G NR air interface is flexible and adaptable, making it useful for the NTN environments. So you can say that NTN leverages standard 5G NR, but optimize it to work efficiently over long distances and dynamic satellite environments. So let's recall what we have learned so far. So first of all, what are the advantages and disadvantages of NTN? So NTN provides extended coverage even to the remote areas, underserved areas. So this helps bringing connectivity to the rural and the isolated regions. Then we have disaster resilience. So in case of disasters, floods, it helps act as a crucial backup. In case of wars, right? It provides global connectivity, right? It can help global connectivity for maritime, for aviation, for oceans, for mountains. It can help in IoT enablement. It help in broadcasting and multicast, right? Global roaming. It helps application that requires continuous communication like transport, such as tracking containers, right? It helps there also. Then we have, in case of congestion, it helps in the network capacity offload, low power capacity, IoT support, and all these things are the advantages we have discussed for the NTN. Also, some of the disadvantages like antenna technology required is very advanced and initial deployment cost is very high. Latency can increase up to which kind of orbits we are using, GEO, LEO, MEO, right? All this. And then we have complex handover and it's depending on the rain attenuation, solar attenuation, all these things, right? Energy consumption may be very high in case of satellites. So, and spectrum is very limited, right? We have discussed, right? After that, we have discussed various kinds of orbits like LEO, MEO, and GEO. For LEO, the altitude can be between 500 and 1200 kilometers, and here between 8,000 to 20,000 kilometers, and GEO 36,000 kilometers. But as we move towards LEO to GEO, latency also increases. In case of LEO, latency is low. In case of MEO, it's medium. Then we have high. But coverage also dependent on the orbit you're using. So in case of LEO, coverage is small. In case of MEO, we have medium coverage. And in case of GEO, we have large coverage. So again, LEO, MEO, GEO. In LEO, we have low latency. In case of MEO, we have medium latency. In case of GEO, we have high latency, right? So as we move towards higher altitude, higher coverage, but higher latency, right? Then we discuss two types of payload. One is transparent payload and one is non-transparent or regenerative payload. So when we talk about transparent payload, we have UE and we have a satellite, which act as a RF repeater. So we have G node B, which is further connected to your core network. So basically, this is your NG-RAN. Then we have this N6 interface between 5G core and the data network. So what exactly is happening in the transport payload? In the transparent scenario, the satellite operates as a radio frequency repeater. So basically, all digital processing that we are talking about is done by G node B. The satellite doesn't alter any signals passing through it in this particular payload, right? So it just ensures the seamless transmission of the data between the feeder link and the service link. And I have already told you what is the feeder link and the service link. So basically the feeder links, which is between satellite and the gateway, right? This is the feeder link, and the service link is between the UE and the satellite, right? Then you have this non-transparent payload. So here satellite plays a central role in this signal processing. That is why we call it regenerative, also non-transparent payload. So you can see here NRUU will be used for bridging the communication between the Earth and the satellite network. The NRU interface acts as a service link. So it will facilitate all user equipments. On the other hand, we have the feeder link. So the feeder link links the satellite using N2 and the N3. You know very well that N2 is between G node B and the AMF, and N3 is between G node B and the UPF, right? So you know very well that in the N2 we have control plane, in N3 we have user plane. In the next session, we'll go deeper into NTN protocols, interfaces, how it is used in the NTN, right? So here in the non-transparent mode, the satellite will be working as a G node B. You can see this satellite act as a G node B. In this payload, G node B actively enhance the signal. It is completely processing the signal, doing various things like demodulation, error correction, modulation, amplification, and the data processing. In this case, operator has lots of advantages like fully control over quality, high data integrity, efficient user spectrum, and the flexible and the intelligent network management. So adding satellite as a G node B, it's very complex and cost oriented, right? So what are the challenges? It is very complex, required advanced onboard processing, higher cost, and power and payload constraints, right? So in the non-transparent payload, satellite, it has some intelligence. It regenerates the signal, acts as a G node B, and enables advanced 5G services between UE and the core network. At high level, you can say that in transparent payload, there is no signal processing, but in the regenerating payload, there is signal processing at the satellite level. Then we have talked about the various operating bands. So there are two operating bands as per 3GPP. One is N256 and one is N255. So 3GP uses these two bands, and these are used for D2D, direct to device satellite connectivity, right? So what is D2D? It means we are using standard smartphones and IoT devices to connect directly to satellites without modifying the hardware of mobile phones. So it eliminates the need for specialized bulky hardware. So this is N255, which is L band, and this is N256, which is S band. So as I said earlier, both bands support D2D. Both bands support handheld devices, right? So here in N256, our uplink is between 1980 and 2010. In N255, our uplink is between 1626.5 and 166.5. And this is the downlink frequencies for N256 and N255. Right? So let's summarize what are the topics we have covered today. So we have like NTN extends, how NTN extends 5G, 6G coverage, how the global connectivity can be possible with the help of NTN for remote areas, rural areas, ocean. Then we have discussed various kinds of mode like transparent mode, non-transparent mode, right? And we have discussed various advantages, challenges of NTN, transparent payload, not transparent payload, fixed beams, non-fixed beam, all these things, right? We have discussed what are the key advantages, what are the key challenges, how the transparent mode work, how the non-transparent mode work. All these things are very important. So since time is very less, so I'm not able to cover the AI part, but we'll try to cover that in the next session as well. So this is the clock in my room, so it says keep learning, keep growing. And as I say in every session that winning requires four parts. One is passion, skills, experience, and targets. With the help of these sessions, you can have the skill part covered, right? So keep training and keep learning until you get it right. Again, friends, this is me, Gaurav Goyal. Please follow me on LinkedIn and you can see my videos on the YouTube as well. Okay, friends, this is all from my side. Thank you all for your time and participation. So, looking forward to the next session. Thank you. Thanks again. Bye.